the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
The Stevens Institute of Technology is proud to present the Hugo New Corporation Sustainability Seminar Series, brought to you by Brown & Codwell, Geocetic Consultants, H2M Architect and Engineers, BEM Systems, and Catalyst Group.
Okay. All right. So thanks for inviting me. It's a pleasure to be here. And as you said, I'm going to present the topic of visual understanding of groundwater contamination. And before I get into the outline and what I mean by that exactly, let's put things into context. Okay, about visualization. So here we see some ocean pollution, right? This, I think many of us have seen this before. This is the Pacific Great, what is it? The Pacific Great Garbage Patch.
Yes.
And, this is easily visualized. If we want to address this problem, it's critical that we can at least visualize what it is. And we could easily do that in this case. Same goes for river pollution. In this case, you see this discharge, an outfall from some plant discharging polluted water. And again, easily visualized. A necessity when developing a strategy to address this kind of problem. But what about groundwater contamination, right? Or groundwater pollution? This is not easily visualized. And it's not easily visualized because groundwater is hidden, right? It's beneath the surface. It's out of sight, out of mind. It's kind of in a black box. So, as I said, visualization is very important. And when I say visualization, I'm not talking about the use of animation to or simulations to quote unquote visualize things. I'm talking about the process of developing mental models, if you will, right? These are kind of visualizations of phenomena in the mind's eye. Okay, and that's something you need when I talk to you about some topic or some physical phenomenon, you imagine something in your mind, you visualize it. So in the case of ocean pollution and river pollution, we clearly have a mental model. For groundwater pollution, as I said, we don't really have one, or many of us don't if we're not in the field of groundwater remediation. So this is my hypothesis, really, is that visualization is needed to optimally manage groundwater resources. And environmental sustainability experts and students, and really the public in general, can benefit significantly from an improved ability to visualize groundwater occurrence and contamination. And again, by visualization, I mean kind of that visual knowledge, that ability to develop a mental model of a phenomenon. Goals here are hopefully to provide you with an ability to better visualize groundwater contamination. The way I'm going to do that is minimize the words and really just prevent visual representations of first the groundwater basics and importance of groundwater, and then use a series of pictures, simulations, and short animations of various groundwater contamination scenarios. So it's very visual, image-rich, consistent with the idea of wanting to foster development of mental models. So let's just go through some fundamentals, hydrogeology fundamentals, very, very, very fundamental. This is you can see a perspective view of a shallow aquifer. Does my mouse pointer work, by the way?
Yes.
Yes,
Okay.
it's working.
Okay, so real fundamentals here. Infiltrating water, that results in a saturated zone, which is referred to as an aquifer. That's our water supply in this case. The top of that saturated zone is referred to as the water table. And if taking a kind of microscopic look here, this aquifer is actually made up of some porous material. Let's say in this case, we have flow actually migrating through unconsolidated sands and silt materials. It's kind of this matrix, this porous matrix. But you can also have flow through fractured bedrock, consolidated sediments such as sandstone, and even through subterranean caves. That's karst terrain. I'm not going to really get into that too much. I am going to talk about fractured sandstone now. Focusing on the stream, you can see that the groundwater is actually feeding the stream. And as far as looking at this from a sustainability standpoint, this is something to consider. That is, the groundwater is actually feeding the stream. It's the source, at least the partial source of water in the stream. So even when it's not raining, this groundwater is really sustaining the ecosystem associated with the surface water, and also the downstream extraction of the surface water that's used for also for municipal supply and irrigation. So the groundwater is a very sustaining resource. Imagine putting in a well. Okay, just a shallow well that just pierces the top of the saturated zone or the water table. And you can see this well in Western Africa, for example, just a shallow, maybe 10 feet. And you can see at the very bottom this water. And that water represents the top of the saturated zone. Okay, so keep that in mind when you're visualizing shallow groundwater. Let's talk about other kinds of aquifers, looking at a place in New Jersey. Here's a zoom in on an oblique perspective, and just to give you some reference, here's Stevens Institute of Technology. That's where we're broadcasting from. This is New Jersey, again, on oblique perspective. And what's underneath us? Well, it's not just shallow aquifers, right? It's a whole series of aquifers, a sequence of unconsolidated sands and silts. And it is these aquifers that are the source for groundwater for the city of Clayton. For example, you can see here, this is a Clayton municipal water supply well. That well penetrates about, let me get my action working here. Okay. So that well penetrates to about 800 feet. That's pumping from multiple aquifers, and that's supplying, there are 4 wells actually supplying about 600,000 gallons per day, just for that, relatively small city. Now imagine when we're talking about the US overall, there are aquifers throughout the nation. Okay, those are represented in different colors here. Keep in mind the white areas, though, there is also groundwater in those areas, but they're typically shallower aquifers. But again, used absolutely for local, private, municipal water supplies. So really, it's all over. We've got 16 million wells, just to give you a sense of how much we rely on this resource. Total groundwater pumped each day, 80 billion gallons. So clearly this is an important resource. On a global scale, same thing. Basically, we've got aquifers all over the world. Those are represented in the different shades of blue and green. And again, keep in mind that those brown areas, there is groundwater at those locations, just at it's less available. But again, keeping in mind, we're talking about groundwater. 99% of all liquid fresh water. That's really quite astonishing. 2.5 billion people use groundwater as the sole source of their fresh water. Almost 50% is for drinking water, and it's a major source of water for irrigation. Okay, so hopefully we're coming away from this little section with a mental image of aquifers, subsurface groundwater, and then what that all means in the context of global water supply. Okay, now let's move on to visualizing actually how plumes or groundwater contaminants migrate through the groundwater. And the first way we're going to do that is to look at a laboratory experiment, a sand tank experiment, actually. So here's the tank. It's probably about 2.5 feet by maybe a foot high. Just for scale, you can see the electrical outlets back here. Here's a sink. This is saturated sand with layers of different permeability material. It's set up such that the flow direction in the saturated sand, right? So there is water flowing through this porous material, and it's flowing from right to left, okay? And these little tubes are essentially acting as wells. Let's focus in on this area. To the right, we're injecting a dye. And you'll see in the subsequent, in this little clip, how that source, we'll call it a contaminant, migrates in the direction of water flow. And as it migrates, it also spreads, right? And that process is called dispersion. So take a look at it one more time. We have the injection of the contaminant at a source. Okay, that was on the right side. And this thing migrates in the direction of flow and spreads. Okay, let's look at that one more time. All right, so now the question, so now that's you have that mental model of what how the contaminant disperses in the subsurface. As far as representing that phenomena of which we cannot see, right? We do that in a couple of ways. One is we can represent it with the color intensity, right? Where the color saturation denotes the variable concentrations. In this case, the darkest red represents the highest concentrations. We can do it using different colors, right? Different colors represent different ranges of concentrations, or sometimes just a single color is used, and that denotes the full extent of, in this case, the dye. Okay. So let's talk about animations now, and I'll go through a series of animations, 4 or 5 animations to illustrate some transport phenomena. There are numerous causes, some of which are shown here. The ones in yellow are the ones that I'm going to show simulations or animations for. So consider this, we're looking at contamination by chlorinated solvents and gasoline from a leaking underground storage tank. Simple cross-sectional illustration. On the left, you see a municipal water supply. It's pumping water. As a result of that pumping, it creates a depression in the water table, kind of from the sucking action, and causing a dip in the water table. Also, the private well is pumping, and that's pulling in shallow groundwater. The groundwater is then discharging to the lake. So that's the hydraulic end of things. Let's now focus back on this factory area. At this location, they're using solvents. There's some release. That dense solvent, referred to as dense non-aqueous phase liquid, that sinks via gravity, makes its way into the saturated zone, into the aquifer. And as it does so, it leaves a kind of a trail of globules of this oil, kind of analogous to, imagine if you would put a dense oil in your fish tank into the sand, it would migrate downward in the sand, but it would leave globules of oil. They basically get caught up in the sand. And that that creates a source such that as groundwater flows through those globules, it results in dissolution and resulting contaminated plume. And you can see here, for example, I'm representing that plume all in one color, but of course you would expect some variability in concentration. It's just a simplification. Let's take a look at this underground storage tank, weathered tank. Gasoline is leaking out. The gasoline is less dense than water. As a result, it generally floats on the water table. Similar to the DNAP, although it also dissolves, and that results in a groundwater plume that migrates to the private well and to the lake. Obviously, the water quality in the home is compromised. Further, the liquid from the liquid gasoline and from the dissolved components in the groundwater, there's volatilization or vaporization of the chemicals, and that can result in vapor intrusion into the basement. So that creates potentially some risk. And also this plume migrates and discharges to the surface water body. It can subsequently absorb to the carbon-rich sediment and make its way up through the food chain, such that some of the organisms in the lake might be compromised. Okay, let's take a look at another animation. This was an animation representing a real site, upstate New York, contaminated groundwater from hazardous waste landfill. And this was really quite a shock to me. I didn't know that such sites existed anymore. This is 2018, a former hazardous waste dump found in the forest, sitting there for decades. And taking a look at some historical maps, found that in fact there were 2,000 plus drums. And these drums were filled with liquid waste, which seeped into the groundwater. So this illustration, or this animation, is just illustrating the direction of groundwater flow from the uplands to the drainage area, and also in the direction of decreasing water table elevation. So that sets the stage for the hydraulics. The excavation, basically we revealed 2,000 drums, which have been leaching for decades, and similar to the scenario I described earlier, the groundwater flowing through that liquid waste results in dissolution and a resulting groundwater plume. Again, note that we're representing the plume in a solid color, thereby defining the overall extent of the contamination. And I should point out something here. When I say contamination, I'm really referring to an impact to the groundwater qualities, so that any alteration of the groundwater quality by that chemical is considered a contamination. But as far as the pollution of the water, that's really more a function of risk. So even though this might be the extent of contamination, the extent of groundwater which is actually polluted, that is, it poses a risk, might be smaller. Okay, so that's important when you visualize a plume or groundwater contamination. When you look at a map, it's important to recognize that those maps might not necessarily illustrate the extent of pollution, but instead illustrate the extent of contamination. It's a subtlety, but I think it's important. Okay, another animation showing flow in fractured rock based on a site in New Jersey where extensive site characterization was performed. So this figure, cross-section showing fractured sandstone and siltstone. This is the top of the bedrock. We've got overburden over here, and this blue line representing the water table. There is a stream, a fault zone, and With regard to groundwater flow, previously we showed in the unconsolidated, kind of more simplified animations, a very smooth flow path. In this case, we have preferential flow because of these higher permeability fractures, such that you have a more tortuous path of groundwater flow. Now, in contrast, there are also places where there are very extensive fractures that are opened over distances of hundreds of feet, and those essentially create preferential pathways, high velocity preferential pathways, so you have direct connection right to that surface water. So you can see that in some systems, you've got quite a bit of variability in the flow geometry, and that plays into how contaminants migrate, as we'll see. So, for example, take a look again, we're talking about DNAPL like before, that's migrating into the open fractures via gravity. And again, as a result of the dissolution, as water moves through that zone, you wind up with a plume that's discharging to your surface water body. Now, in this case, we're using the variable color scheme to denote the variability in concentrations, which makes it clear that you've got higher concentrations in these preferential pathways. So this gives you a more detailed representation of the distribution of contaminants and how they migrate. And that might be important to know if you're going to go in and try to remediate this plume. You need to know those details so that you can see where you want to target remedial technologies. Another animation, or actually this is a simulation, computer simulation of site remediation in Ohio. So this is the site, the extent of the site, and this shows the ambient groundwater flow. That is, this is the direction of flow during the decades of operation of this former facility, which is not shown on this map anymore. It was contaminated. As a result, they installed 4 extraction wells, and those extraction wells are pumping the groundwater such that they capture the groundwater. They no longer, they essentially prevent the further off-site migration of groundwater. And they do that to restrict the further migration of the groundwater plume. So here on the top, you see a timeline. You see the animated changes in the groundwater plume extent. It's shrinking because of the extraction of that groundwater. So basically, we're predicting by 2046, as a result of that pumping and some natural degradation of these compounds, off-site remediation will be complete. So this is previously we visualized, we started to develop our mental models of what these plumes look like in cross-section, that is kind of in the vertical extent. This is showing the extent in map view. Okay, but you can get a sense now that this is a map view, but there is a vertical distribution as well that we're not seeing. But you can imagine that we're not talking about contaminants that are right at the surface. These are contaminants that are in the form of plumes under the surface. Let's just take, I know that was a little quick, so I'm just going to run that animation again. We've got the 4 capture wells. They're pulling in groundwater, preventing further migration. This is the original plume extent. It already is off-site. Start the pumping by 2018, I believe, or 2019. We've already got a reduction in the footprint, and it's projected that we'll get full off-site remediation by 2046 as a result of the continued pumping. Okay, so that's another animation to help us build our mental model of how these contaminants, or how groundwater contaminants migrate. The next animation, let's see how I need to do a little bit of a change here. I need to share my screen again. Okay, now we're going to talk about contamination by firefighting foam. Yeah, a little bit of a. Are you seeing it? Do you see my screen that shows multiple pictures?
Yes.
Yes.
Okay,
Yeah.
great. Okay, so we're talking about firefighting foam. And by firefighting foam, I'm referring to something called aqueous film forming foam, or AFFF. And that's used extensively at airports, military bases, and you can see essentially they're spraying a combination of foam and water. The top left, you've got, they're doing some nozzle testing. The foam is on the tarmac that's often runs off into the stormwater sewers. On the right is actually showing a fire testing area. That's where they have mock fires, essentially. That's just a fuselage in the top right there. They start the fire and then they basically test their strategy and their equipment to put this out. Similarly, we have another testing facility in the bottom left. This helicopter here, that's a use of AFFF on an actual crash. This bottom, this picture right here is in a hangar. There are fire suppression systems where they basically test these systems. You see that just dumps foam till the hangar is fully covered. But there are accidents where the foam is release, and it does make its way out of the hangar and of course into the stormwater sewers, which might be unlined, or into the grassy areas. We've got an example here of putting out some other fires. So the AFFF is used for fuel-based fires, again, extensively at airports, military bases globally, and it's been used for decades, since the 1970s. And in fact, it's still being used, although they're changing the formulation. So the AFFF is composed of per and polyfluoroalkyl substances, otherwise known as PFAS. This is a hot topic. It's been in the news a lot. Movies made about it. It's present in groundwater nearly everywhere, or I should say most places, and people are getting pretty excited about it, not happy about it. There's a lot of investigative work and remediation work to be done. Here are just some of, and really PFAS are special in that they're oil resistant, water resistant, heat resistant, degradation resistant. They're very stable, and that makes them very useful chemical for manufacturing, and in fact also for this firefighting foam. So as I said, as I'm pointing out here, there are thousands more. The ones that receive the greatest media coverage are PFAS and PFOA. All of these other ones, they're slowly getting more and more attention. But we're not going to talk all about those. We're talking about the firefighting foam. So the PFAS, they're being referred to as forever chemicals because of this resistance to degradation and their stability, and the fact that they're bioaccumulative. So that's why they're being called forever chemicals, made up of many different individual chemicals. So let's take a look at this scenario. 3D perspective of this area where there's a military base or a commercial airport. They have these fire training areas, as I pointed out before, where they have these mock fuselages. They set a fire. The zone represents the flooded foam. As a result of that, oh boy, internet connection is unstable. Everyone with me?
Yeah, everything is fine here.
Okay, so we've got that fire training area. As a result, you've got leaching of the solution, the AFFF solution, and the resultant plume. Okay, and I should point out, as I said before, the way that plume is being represented with this color variability, right? This kind of color gradation. But just note that it's not actually a plume with color, right? It's actually colorless and odorless. We're using the plume as a representation of the variable concentrations. So taking a look at the actual infiltration process, I set up a little kitchen experiment here illustrating what we're talking about with regard to infiltrating AFFF. It's not that the foam is penetrating the soil. Rather, when you spray the foam is collecting on top of a solution of surfactants. Literally, I'm using dishwashing liquid here. So you have the solution, this is soil. So it's this solution, which essentially has the dissolved PFAS constituents that leaches into the soil. And that's what results in the groundwater contamination. You don't have foam entering the soil per se. What the soil does, some of the surfactant does partially absorb to the soil. And that's significant because even when these fire testing areas have not been used for literally decades, 20, 25 years, that absorbed surfactant in the soil effectively acts as a continuous source. So these plumes are still emanating from these areas that haven't been used for decades. Now, obviously, this plume is discharging to the surface water and potentially impacting the ecosystem. This private well is being impacted because it's screened right into the plume. However, in this case, this municipal well, like the wells I showed you in the New Jersey, some of them are screened deep in what's called a confined aquifer that's hydraulically isolated from the shallower groundwater, so that in this case, the municipal water supply is not being contaminated. That's not always the case. Certainly, there are locations where the municipal water supply has been impacted. And typically the impacts are occurring with regard to AFFF, the impacts are typically closer to the airports and military bases, but it could be over distances of kilometers. And that could be the scale of a plume like that. Okay, but it's not just the fire testing area, right? We have multiple release areas. We've got the fire training. We've also got the suppression system and the hangars, which we have accidental releases. And then we actually have the use of the firefighting foam at accident sites. And as a result of all those releases, then we've got multiple sources, right? So now looking at it kind of in map view, we've got plumes, multiple locations, all discharging to the surface water body. So we're not talking about discrete plumes typically at a site like this where you have multiple. It's really quite a bit of coverage in terms of the impact of groundwater and the discharge to surface water. So for example here, this is a PFAS concentration map, groundwater concentration map at the Wurtsmith Air Force Base in Michigan. This is a pretty well-known site, very well characterized, and you can see they're using this color variation to show the distribution of PFAS. And those hot spots, in this case, the darker areas, coincide with, for example, this was a historical accident area. This very dark area was, I believe it was a sludge pond where they dumped their treated wastewater, which still had PFAS in it. And these other areas close to historical sources. And you can see these are all discharging to surface water. Okay, so now hopefully when we start looking at maps like this, we don't just see some blobs here. We have a mental image of what's happening at the surface in terms of releases, but also maybe a 3D perspective and a two-dimensional cross-sectional perspective of how the contamination is migrating. Let's talk about the foam migration, right? So you have the foam at the surface, it's running off through the stormwater sewers, overland flow, and actually you see it on surface water bodies here right along the lake shoreline. And you see that foam even during periods when they're not actually spraying. It's, again, like I said, this surfactant is dissolved in the water, and essentially much like if you had dissolved soap in water and you took a whisk to the water, you could make bubbles in the same way bubbles form in surface water with the creation of waves through, wind, for example. So summary as far as AFFF contamination at military bases and airports, right? We have the use of the AFFF at fire training areas. Then we have accidental releases. We've got the actual use at accident sites. We have the resulting groundwater plumes, formation of foam on surface water bodies, and we do have an potentially impacted surface water and result in some threat to the ecosystem. Here you do see in some places, do not eat the fish signs. Now, they also use these at refineries, as I said, and this is basically the same image, but just showing a layout of a refinery. Same scenario. In this case, I don't have the plume on here, but the plume would be exactly the same. I mean, as far as illustration purposes. Another element I've included here is the wastewater treatment plant. So the runoff water from the fire training area, and actually from all of the berms, the water that's collected in all the berms around the tanks, that all gets discharged to an on-site wastewater treatment plant. It has dissolved PFAS in it, right? However, those treatment plants weren't designed, and most still are not. Now, maybe they're starting to upgrade them very slowly, but for the most part, none of them have been equipped to treat the PFAS. So that just basically gets discharged to the stream, and you've got the same issue. You might not have the foam, but you certainly have the dissolved PFAS that are bioaccumulating in the lake and in the river. So to wrap it up, what am I hoping I hope you're taking away an improved visual understanding of groundwater contamination by way of us looking at animations and simplified representations of these flow phenomena. So I really thank you for your attention. Please contact me anytime, and I'll take any questions. Thanks so much.